So this is joint work with Shalev Ben David, and this is the archive number in case you're interested. So the topic is related to digital signatures, so this is just a quick reminder. Digital signatures mimic the properties of handwritten signatures and quantifies things from a computational perspective. It is computationally easy for the signer to sign a document, in this case using the secret key. It is hard to forge a signed document without the secret key. And there are two variants for digital signatures, a private and a public one. The private one is often called message authentication code. And the property is that it is easy to verify a signed document using the secret key in the private setting and the public key in the public setting. So our variant is called quantum tokens for digital signatures. And it cannot be constructed classically. And I'm going to present an illustrated version of the abstract of the paper, which is in the form of a fable. The fisherman caught a quantum fish. Fisherman, please let me go, begged the fish, and I will grant you 3 wishes. The fisherman agreed. The fish gave the fisherman a quantum computer and 3 quantum signing tokens. As you can see, this is a fairly simple quantum computer. We only need a depth 1 quantum circuit for signing. The fish explained, to sign your 3 wishes, use the tokenized signature scheme on this quantum computer, then show your valid signature to the king who owes me a favor. The fisherman used one of the signing tokens to sign a document, give me a castle. Now, I want to emphasize, this is a classical document. Here you can see the signing token. This is a catch with a rubber stamp in it. And once the message is signed, the signing token is consumed. And the signed document is, again, just like classical digital signatures, it's entirely classical. The signature itself is classical, and of course, the document is classical. And rushed to the palace. The king executed the classical verification algorithm using the fish's public key, and since it was valid, the king complied. The fisherman's wife wanted to sign 10 wishes using the 2 remaining signing tokens. The fisherman did not want to cheat and secretly sailed to meet the fish. Fish, my wife wants to sign 10 more wishes. But the fish was not worried. I have learned quantum cryptography following the previous story, The Fisherman and His Wife by the Brothers Grimm. The quantum tokens are consumed during the signing. Your polynomial wife cannot even sign 4 wishes using the 3 signing tokens I gave you. How does it work? Wondered the fisherman. Have you heard of quantum money? These are quantum states which can be easily verified but are hard to copy. This tokenized quantum signature scheme extends Aronson and Cristiano's quantum money scheme, which is why the signing token cannot be copied. So to recap, what's the challenge the fish is facing? The fisherman should be able to sign at most 3 wishes. Of course, the fish could simply give the secret key to the fisherman, but then the fisherman would be able to sign to have as many wishes as he likes. So this is not a good solution. So the goal here is that each signing token should allow to sign only 1 arbitrary message. And of course, this cannot be achieved classically. OK. So how can we abstract this primitive? So in many cryptographic schemes, we have a key generation step, and then some operation that requires the secret key. So in a tokenized scheme, we want to have the same step, but then an intermediate step that takes the token generation algorithm, which takes the secret key and outputs a token. And you can, just as before that you could apply some operation, we still want to apply this operation, but using only the token. And that each token can be used only to apply a single operation. And the hope here is that this operation should, due to destructive effects of measurements, should consume the token. And indeed, we achieve this for private digital signatures, MACs. And we give a plausibility argument for a public tokenized signature scheme. The original construction we had is essentially broken due to an attack on the underlying quantum money scheme by Aronson and Cristiano. Unfortunately, I won't have time to get into this. So now to a formal definition of a private tokenized signature scheme. So we have a key generation step, which generates a secret key, a token generation step, which generates the token, and a sign, which takes a token and a message and outputs a classical signature, and a verification algorithm, which takes the message and a signature and outputs either accepts or rejects. And the correctness property that if we take a valid token and sign it at the message M and then verify, it of course should accept. And the security is the following. If you're given n+1, it is hard to generate n+1 unique signed messages from n signing tokens. And this is the formal definition for that. So the first step is we show a reduction to a simpler task, one time one bit tokenized signature scheme. So one time means that it is only hard to generate 2 unique signed messages from one signing token. And 1 bit means that we only need to sign a single bit documents. And we show that given a one time one bit private tokenized signature scheme, and assuming a collision-resistant secure hash function, then we can construct a tokenized private signature scheme. And similarly for the public variant. And the proof ID is some known techniques related to quantum money plus the hash and sign, classical hash and sign paradigm, which is used classically. So basically the main challenge is to construct this one time one bit tokenized signature scheme. And I'll explain how this is achieved. So in order to explain that, I'll need a few preliminaries. This is fairly simple ones. So we suppose you have some subspace of f2 to the 2n. A dual is the set of all vectors in f2 to the 2n that the dot product with it is 0 for all elements in A. And it is known that the dimension of A plus the dimension of A dual equals the dimension of the entire space, which is 2n here. It is also known that given a basis for A, it is easy to generate the uniform superposition over all the elements in A. And if you apply a Fourier, the Hadamard tensor 2n to the state, you get the uniform superposition over A dual. And of course, if you measure A, you get a sample from A. And if you measure A dual, you get a sample from A dual. So how do we use that? So the construction is the following. Key generation, it simply outputs a random subspace of dimension n. Token gen takes this subspace and outputs a uniform superposition over it. And now, how do you sign? So to sign the 1 bit, which is 0, you simply measure in the standard basis. And to sign the bit 1, you measure in the Hadamard basis. And how do you verify? Now, of course, if you measure in the standard basis, you get a random element from A. So here you simply check that the signature is a non-trivial element of A. So you just 0 here is a special case which should happen very rarely. And similarly for 1, you just check that the signature is a non-trivial element of A dual. So in order to prove security, our first result is a query complexity result. We show the following. Suppose A is a random subspace of f2 to the 2n of dimension n. And suppose you're given Oracle access to membership in A dual, and 1 copy of the state A. Then it takes exponential time to find both an element in a non-trivial element of A and a non-trivial element of A dual. And note that it is, of course, trivial to find a non-trivial element of A or a non-trivial element of A dual. So, and what we show is that it's hard to do both. And the proof technique is based on the adversary method, and the intuition is strongly based on the no cloning theorem. Of course, if you could clone the state A, then you could apply, say, Hadamard tensor n to the second copy, and then measure both systems and get one element of A and another element from A dual. And essentially, you have to do that. You have to use your queries in order to somehow get your second copy, which takes exponential time. And how do we use that? Then it's a simple corollary that the 1 × 1 bit scheme is secure because of this square complexity argument. Here's why. If you manage to output both a signature for 0 and a signature for 1, it says that you must have found a non-trivial element of A and a non-trivial element of A dual. And we prove this is impossible, right? It takes exponential time. And the access to the verification, the verification oracle is exactly membership to A and A dual. And the previous results simply said that this takes exponentially many queries, and therefore it cannot be done efficiently. So what about public tokenized signature scheme? So as I mentioned before, our construction is strongly based on some earlier construction by Aronson and Cristiano, which is unfortunately broken. The attack itself is reported in our paper, and we kind of give a plausibility argument for a different construction, but it's not a very there are no good reason to believe that it's secure. Let's put it this way. So we can prove security if there exists a strong form of obfuscation called virtual black box obfuscation, and we further need that it has the property that it's secure even under quantum-dependent auxiliary inputs. There are some positive results in that direction. Unfortunately, they cannot be used because we need a quantum secure one, and this one clearly isn't. If we have an obfuscation, in general, obfuscation is a way to take a program and compile a different program, which is unintelligible in some way. So it on the one hand should allow you to evaluate the function. In our case, it would be, oops. The functions are this membership function, so you should be able to evaluate these memberships in order to verify the signature, but nothing else should be, you can't, for example, find a basis for it just from looking at the obfuscated program. So if we had a virtual black box obfuscator, this would be the public key. Unfortunately, we don't have candidate constructions for it, and there are candidate constructions for a weaker form of obfuscation called indistinguishability obfuscation, and we conjecture that this is you can use instead of using here VBB obfuscation, you can use indistinguishability obfuscation. So some extensions and applications. So we show how our scheme can be revocable, meaning if someone holds suppose that the fisherman holds his signing token and he wants to, he says, well, I don't want this token. So we can bring back the token to the fish, and the fish can revoke it. In other words, to make sure that indeed the fisherman hasn't used its token. And this is useful for some scenarios. It can also be used to send quantum money over a classical channel and to forbid something which is called the two-faced behavior in distributed computing. You can look at a paper for more details. And some open questions. So there's a tightly related topic, related to quantum money, which is kind of the work here, which is called quantum copy protection. Here you want a compiler, which takes a classical program and outputs a quantum state. This quantum state could be used in order to evaluate the function, but in a way which does not allow you to share this program with your friend. And we don't have good candidates for, we don't have any candidates for that except for very few cases, essentially point functions. Another open question is tokens for other primitives. One interesting thing would be tokens which are used to decrypt a message. So imagine you go on vacation and you give your friend your ability the ability to decrypt your message, but once you're back, you want the token back, and then you're not afraid that he'll be able to use it again. Again, we don't have a very good candidate construction for the public version, and we're looking for one. And we also don't have I mentioned in the previous slide that it solves some problem in distributed computing, the two-phase behavior problem, but I'm not aware of any improvement that can be gained from such a solution. Sorry? Oh. That's it. Thank you.